Hi, everyone. As you can see from the slide, today we have a topic about issuance and mining in Bitcoin. And actually, we are going to have not one, but I would say 1.5 lectures because the topic of issuance is not really comprehensive and is not really complex and can be covered in quite a brief time period. So let's don't waste any more time and get straight into it. First of all, when we are talking about issuance, we mean the monetary issuance. So this refers in the context of Bitcoin or any other digital currency, and even with fiat currencies, to the process of releasing new coins. So first of all, when we are talking about fiat currencies such as hryvnias, euro, dollars, etc., they are issued by being printed on a special facility and then distributed among the people of the country using the banks. But in Bitcoin and in other digital currency systems, the process of issuance is decentralized, which means that it is not regulated by any party and regulated by the algorithm itself. And the process of issuance is done by the members of the system themselves. But whenever we are talking about issuance of the coins, we mean the process of releasing new coins and making them available for being used. And we will talk about differences in issuance processes a bit later, but for now, this is all that we have to know. Now, a little bit about the numbers, actual numbers of how many Bitcoins there should be at the end of the day. And as you may already know, is that the issuance of coins in Bitcoin is limited. So Bitcoin has deflational nature, which means that coins cannot be issued forever. We have not we we don't have 21 million of Bitcoins, but the protocol rules specify that there cannot be more than roughly 21 million Bitcoins, or if we want to be really precise, then this number of Bitcoins. And this is the same number, but calculated in Satoshis. And Satoshi, if you don't remember, is the minimal unit of accounting Bitcoin. So this is like, you can think of it as a cent, dollar or euro cent. And in reality, even when the issuance is finished, there will be actually less than this number of Bitcoins. And we will mention the reason why once we get to this problem. But just so you know, if the upper bound of Bitcoin specifies that there cannot be more than roughly 21 million, it doesn't mean that at the end of the day, when mining fees are over, it doesn't mean that there will be this exact number. Now, as for the issuance of Bitcoins, on average, as you may imagine, new coins appear once every 10 minutes. And this is happening when the new block is added to the blockchain. So initially, the reward for the block, which was specified in the software of Bitcoin, was 50 Bitcoins. At the day when Bitcoin started, it was 50 Bitcoins. But then every 210,000 blocks, the number of new blocks of new coins is halved. So it becomes 25, and then so on and so on. It is decreased to by 50%. And if we extrapolate this notion of every block appearing roughly every 10 minutes, we can make an educated guess that this halving process happens in 1,458 days, which is roughly almost 4 years. Once halving reaches the smallest division unit, which is 1 Satoshi, it will stop and the block reward will be simply 0. So once we finally reach block reward of 1 Satoshi, the next halving will simply set it to 0, and there will be no Bitcoins issued, and the only material, the only monetary incentive that validators will be receiving will be the fee for the transactions in the block, no new issuance of Bitcoins. And interestingly, at the current moment, over 90% of all Bitcoins have already been mined. And if we look at this graph, on the x-axis we have the time, and on the y-axis we have amount of coins in millions. So right now we are at the beginning of 2023, so we can look at this graph and guess that it's somewhere above 18, maybe closer to 19. So now we have almost 19 million coins roughly, and the number will grow slower and slower and slower up until it eventually reaches the top, the ceiling of the total number of issued coins. But you can see that from 2009 to 2013 it was a very fast jump. So here the line is very steep, then it becomes smoother and smoother and smoother and smoother, and it goes on until it reaches the end. There have been already several halvings in Bitcoin. The first was in November of 2012. Then the reward for the block became 25 Bitcoins. So the next halving, as you see, the first one was in November of 2020, and the next one was in July of 2016. So roughly 4 years. And then the block reward became 12.5 Bitcoins. Then in May 2026, 25 Bitcoins. And the fourth halving is forecasted for April 2024. And when this happens, the new reward for the block will be 3.125 Bitcoins. And such a gradual approach exists to decrease such gradual approach in decreasing the pace of issuing new Bitcoins exists to allow validators to get used to this deflational process, to the deflational nature of Bitcoin as a system. Reward is still necessary because otherwise, well, no one is running Bitcoin nodes out of charity, right? People want to make money, and that's why there should be and there will be a certain monetary incentive, and this monetary incentive will be fees that will be gathered from transactions, but it's not like we just flip the switch and say that starting from today, the reward for adding a new block to the blockchain will be 0. No, we have this very gradual process which allows Bitcoin to grow and evolve as a system naturally, not with a flip of a switch. Now let's get a very brief reminder of a Coinbase transaction. So each block has a so-called Coinbase transaction, the transaction number 0. And in this transaction, the block creator, meaning the validator who has generated this block and proposed it and was able to successfully add the block to the blockchain, can assign coins to his address, but the total number of reward for the block cannot be more than the amount of these issued coins plus the fees that are collected from the transactions. However, if the validator does not specify where to output this block reward, it will be lost forever. So it will not be unlockable ever, and these coins will be simply lost. And that's why before we were saying that the total number of bitcoins at the end of the day will be less than 21 million, not exactly 21 million. And this is one of the reasons why. Now let's look at an example of Coinbase transaction. So this is just a screenshot from the Explorer. It's in human readable format. It doesn't have to really look that way, but it is for us to see and to make sense of what is going on here. So in addition to what we have already defined, important thing to know is that Coinbase transaction has no inputs. So inputs are either empty or filled with arbitrary data, because Coinbase transaction is not really unlocking or spending any outputs, right? We are literally issuing new coins out of nothing for this process of successfully generating a new block. We are issuing these coins, and that's why inputs are never verified. So even if I, as a validator, have written something in the inputs of Coinbase transaction, no one would look there. So even if you want to, you can put some arbitrary data there, like a memo or something. No one will look there anyway. I mean, in terms of the protocol, it will be still valid, because no one really cares about what is happening in the inputs of Coinbase transaction. Then, as I have said, outputs can be either zero, which means coins will not be issued, thus the coins will be effectively destroyed, and no one will be able to use these coins. Or validator can specify the address and receive coins to this address. Interestingly, around 10 to 15% of all the coins that have already been issued are considered to be destroyed, meaning they cannot be spent. And of course, this is an estimate, and we cannot really make a precise calculation and know exactly how many coins are lost forever. Maybe someone did that, but it would require certain, it would require to gather statistics and gather transactions and do these calculations of outputs, whether they are spendable or not. And sometimes it's not really easy to know whether the output is spendable or not, but roughly this is the number, and this is due to different reasons. Sometimes people put incorrect spending conditions. Sometimes people do what I've said and put zero in the output, so they do not issue the coins. And well, some reasons as well include losing the access to the private key, but this is impossible to prove and impossible to see whether this output is cannot be unlocked because someone lost their private key, because we will never know that. Now let's see how Issuance is compared to other systems, to other accounting systems. So in Bitcoin, it's clear the total volume is around 21 millions, and the issuance of coins is reduced by 50% every 4 years. We got that out of the way. Now let's look at Ethereum. Interesting peculiarity of Ethereum is that the total volume is unlimited. So there is no cap, there is no ceiling on the total volume of Ethereum coins. And the method is that here we have two reward is to others, but Ethereum has, in fact, a certain mechanism that allows it to estimate the appropriate reward for the next time period. So Ethereum has a formula for the number of coins that will be issued during the next year. It is calculated as roughly 1 or 2%. You can look it up if you want to. I mean, the exact percentage, you can look it up. 1-2% of all coins that have already been issued is taken. So if we have 2 billion coins, for example, they have been issued for the past year, we take 1%, and this will be the total number of coins to issue in the following year. Then we divide this number by the number of blocks that will be added, again, by estimating that, and get the average block reward, which is, of course, will slightly differ. But this is relevant for proof of work, for when Ethereum was proof of work. But since then, since the great fork, the rules have slightly changed, and so is the reward has slightly changed. As for the Dash, which is another cryptocurrency accounting system, the total volume is a bit smaller than in Bitcoin. It's 19 million, around 19 million, and issuance decreases by 1/14, which is approximately 7.14%, every 240 blocks. And since blocks in Dash are added faster, so there's smaller gap between the blocks, it happens approximately every 383.25 days, which is roughly slightly more than a year. So Dash has this decreasing method more often, but it's but the issuance is decreased by a smaller degree. So it's a different approach that they took. And what is important in all of these three systems is that issuance is done in a decentralized manner, meaning the rules are decentralized, the participants are decentralized, and everything, the whole process of issuance is decentralized. So in Bitcoin, in all of the systems, the one who finds the blocks issues the coins for themselves as the reward. The rules of issuing the coins are in the protocol, and everyone follows them. So they are also decentralized in a way. But when we look at a fiat currency, which is, again, any currency of a legal currency of a country, be it a dollar, euro, hryvnia, or whatever, the total volume is unlimited. So it's inflational in nature. Meaning that the more money we print, the smaller the value of one single unit of this currency. And the issuance method is by central bank. So as I have mentioned, there is this facility, this typographic special facility, which does the printing, and then the banknotes or the coins that are minted again on a special facility are distributed in a centralized manner among the banks and among the citizens of the country. So this is the difference. And now we are done with the issuance. If you have any questions, write them in the chat, but I will not wait too long for new questions because we still need to get through the mining. And before we start talking about the new stuff, again, a very small reminder is the block structure. So we have the block. The block has a header, and the block has an array of transactions. The most crucial is that the header of the block includes the hash of the previous block, but more commonly it includes the hash only of the block header, since the block header has already hash value of all transactions included in the block. So here is the hash of a previous block. Then once a validator constructs the block, gathers transactions inside of the block, everyone is free to vote whether they approve or disapprove, agree or disagree with this block. And this is the way the system decides whether to actually add the block or not. So, for example, if this block is valid and all transactions are valid, we expect at least honest people, at least honest validators to approve this block, to accept it, and to also add it to their blockchain chains of blocks. Now, as for the proof of work. Interestingly, the proof of work mechanism itself was created not by Bitcoin, and in fact, it appeared way before Bitcoin was even proposed as a white paper. The term itself first appeared back in 1999 in the journal called Communications and Multimedia Security. Basically, proof of work was proposed as a way to protect network systems from abuse based on the system is protected from frequent requests by making the client to do some computational process which takes time and takes the resources completely. So basically, you are creating a bottleneck for your users, acting as a spam blocker. So you cannot DDoS my system if I have proof of work, and to make each request, you need to, your computer needs to spend, I don't know, 30 seconds or let's say 1 minute doing this proof of work, because you will be able to make requests not more than 1 request per minute. So you cannot flood me with requests, have 1,000 requests per minute or 100,000 requests per minute, only 1 request per minute at the very best. And in order to do a DDoS attack, in such case, you will need an enormous amount of computers, because each of them can make a request only once per minute. And the thing is that this computational proof of work thing is done on the device of the client. So it's not the server side function, it's not done on the server, it's a speed bump for the client. So the client is busy doing this task, and only once the task is successfully done, the request can be completed and accepted. And the main idea of proof of work anti-spam mechanism is that it should be computationally complex to generate the proof, but extremely easy to verify the proof. And we will see how it works at the example of Bitcoin, because verifying proof of work is very, very simple and computationally easy task. So you do not need to spend equal amount of time verifying proof of work. You can done it in a single moment. Also, similar approaches are called client puzzle, computational puzzle, or CPU pricing function. One of alternative ways to implement proof of work is the process of searching for prime numbers. It was implemented in Prime Coin. And in order to complete proof of work based on searching for prime numbers, you need to find the next really large random prime number. The larger the number you need to find, the longer it will take. But disadvantage of such an approach is that a verification function for checking whether the number is actually a prime number is not as straightforward, and that's why it requires more computational power. So it's not as effective as hash-based proof of work algorithms like the ones used in Bitcoin and in other systems. One of the examples of blockchain-based accounting systems that use prime numbers proof of work is called Prime Coin. It does not exist anymore in the way it was. I have checked today before the lecture, and They do have some website, they do have this promotional materials, promotional copywriting text on their website, but honestly, I am not sure whether it is the same Prime Coin and whether it is even a legit website. So proceed with caution if you want to learn more about Prime Coin and maybe play around with it. Now let's at the example. Here, imagine that hello world is our block header, which it is the value which we have received by hashing all of the transactions in the block. We cannot change this value unless we change transactions in the block, and we do not want to do that because we have set of transactions that we want to include in this block. But there should be a way to do this to generate many hashes, many different hashes with the same base data. So in this case, hello world. So we want to generate a valid solution to the proof of work puzzle, having hello world as our text. And to do that, we add the value, an index value, which is called nonce. So here, 0, 1, 2, so on, so on. We just increment it until we get the required value. So for example, just imagine that for this computational puzzle, the resulting hash value should have 4 zeros here as the significant bytes. So let's say that here we have most significant bytes, and the 4 of them should be zeros. Since hash functions work in such a way that even if you change one character, one very small, one bit of the input, the output will be completely different. And that's why basically what is happening here is that we are incrementing this value. It doesn't really mean anything for our transaction, but it allows to generate a completely new hash value every time. So for every iteration that we have going on here, is that this hash will be different, but we can separate them. This remains the same, and this just gets incremented. So the moment we reach this point, when the nonce is 4,250, we get the required hash, and then in order for the validator to make sure that we are not fooling them and that this is a legit result of computational puzzle, what they do is they simply hash this value. So they take hello world, they add the nonce that is also included together with this value, and they get exactly the same hash value which should be there. So we have 4 zeros at the beginning, which the proof of work was completed. Of course, you don't have to increment. You can do it randomly. You can, I don't know, add something else. You can add numbers and characters or whatever. But this approach is the one which is the most easy to verify and the one that makes the most sense in terms of the requirements of this proof of work. Now let's have another refresher, this time about the block header. So version is the protocol version, takes 4 bytes, hash of the previous block 32 bytes, hash of the Merkle root of transactions also 32 bytes, time stamp 4 bytes, bits, and it's important, bits is a compressed version of difficulty parameter. It takes 4 bytes, and it will be important right now. And the nonce, this proof that we have generated a new hash value, is also 4 bytes included also in the block header, so that others can verify whether we have done the proof of work or we are trying to cheat. Now, about the difficulty parameter. So what's up with all these bits and what's up with all this difficulty? How does it work? So here we have bits parameter, this compressed difficulty, which eventually which is received from this target. But let's go step by step. We have the target difficulty. This is called the target difficulty. It is a 256-bit string, and the resulting hash value is compared to the target. So it is matched against this target. Its significant bits right here, they go here, most significant bits on the left, they must be zeros. And the remaining value, which starts here and goes to the least significant bits, must be smaller than it's 0404 CB in hexadecimal. So, and here we don't really care. So this notation here, 0404 CB, is the ceiling, the top boundary for our hexadecimal number, our hexadecimal value. And everything which is going on here doesn't really matter as long as we have zeros here and this value here. And by manipulating this value, so by adding or removing zeros or by changing this value, we can manipulate the actual difficulty of mining. So this is the determiner of how difficult it is to mine, to find the for a block at a given time. So having this parameter, we can derive target from. So we take the rightmost byte and subtract 3 from it. So this is just a notation. So the reason we are subtracting 3 is to shift the value and make it easier to use. Then and this is like this is the resulting value, and this is the formula how the difficulty is calculated, just in case I jumped too quickly. So we take this, subtract 3, thus we shift the value, and then we multiply the result by 8, which means a number of bits in 1 byte. And this shifts the value from the right least significant bits to the left to more significant bits. So we are doing this shift again. So we shift the value from the least significant bits, and we push it to the left here. And this is how we get this boundary here. So we push it all the way to the left. The precision is defined by these 3 bytes. So if this is the the byte from which we derive the difficulty, these 3 bytes are used to derive the precision. So you see CB or 0404, and here we have 0404 and CB. So these are unpacked and used for this precision, threshold in our final target. And since hashing algorithm is irreversible, it is impossible to know what nonce will satisfy these conditions unless you find the actual nonce, unless you do the work and find the value by hashing and hashing and hashing and hashing until you get the necessary value. So you cannot first construct the hash that you need and then say, okay, if I want to get this hash which would satisfy the conditions, I need the nonce to be 4210, for example. It's impossible due to the nature of hash functions. And the reason why this bits parameter exists is instead of keeping this very big value, we can have only 4 bytes, 1, 2, 3, 4 bytes, as we put it here. And these 4 bytes include all of the necessary information in order to understand what will be the difficulty, what is the target difficulty at which we should aim. So I hope it was clear. And let's move on to the spam protection. So as you have already got it from the initial mention about proof of work, it acts as the spam protection. And in Bitcoin, it allows to prevent threat actors to create a big number of blocks and basically overload the system. So in order for the block to propagate through the network, its creator must prove the right to vote. And this whole proof of work mechanism is the proof of vote in Bitcoin. So in order to participate in the voting, you need to prove your engagement into the system by acquiring the appropriate hardware, which is sufficient enough for you to generate this vote for you. So you complete the proof of work successfully and you get the voting right to add a new block, to add the block you consider correct in the current round of voting. So your proof of work nonce is your vote. And in Bitcoin, voting rights are proven through this solution. It's the spam protection, and it's the approach to prove your right to vote. And the process of solving a problem is called mining. The hardware for solving the problems is a miner. So we have hardware miners doing the mining, and the party, the person, organization, or whatever who owns and maintains the hardware is the validator. So mining is the process, miner is the hardware, and validator is the one who stands behind the miner. Right now, mining runs on specialized hardware. We will have a small historical brief later. So it runs on a specialized hardware. Mining is rewarded with coins. This reward is for maintaining network reliability. The reward consists of new coins and the commission fees, the fees that are included in the transaction. But I believe by now you should already have a good grasp on this transaction fee concept. And the complexity of a resource-intensive task is adjusted so that the blocks appear at a constant frequency, or at least they are aimed to appear at a constant frequency. Having more computational power doesn't mean you don't have to oblige by the protocol rules. So you cannot just say, I have enough computational power, I can do whatever I want. No, it means that your blocks still have to be valid. If you have big computational power, it means that you can choose which correct transactions you want to validate and include in the block. You cannot just add gibberish into your block and expect that your enormous computational power will allow you to propagate this gibberish through the network. No one will simply accept it because it violates the rules of the protocol. Now, as for the hardware, let's talk about the hardware. When Bitcoin only appeared and people didn't really care much about it, it was effectively costed $0, €0. It wasn't able to buy anything. So people just came and went and looked at this funny new thing, this funny little cryptocurrency, this funny little Bitcoin thing, which was mostly for enthusiasts. And that's why it was possible to do the mining process on a regular computer or a laptop with a CPU. CPU is a general processing unit. It can be used for a variety of tasks, and it can do practically any computations that we can think of in the modern world of computers. CPU can do that. The other problem is that CPU is not really effective at doing that. So although it can do a lot of different things, it's not really effective at doing any of them. And that's why when the price of Bitcoin started growing, people realized that it can be more efficient to use GPUs for mining. And since GPUs have multiple cores working in parallel, and they have just enough cache memory in each core to generate SHA-2 hash values, it was possible to use them as the hardware which does the mining process. And some smart people modified Bitcoin software to support GPU mining. So here we have just a regular motherboard with a CPU and with everything. It runs Bitcoin node software, and this software is modified so that the mining process is handed over to an array of GPUs instead of being handled by the CPU. And this allowed to significantly increase the effectiveness and to do the computation faster. And this is called a mining rig. So this whole thing is called a mining rig. The rig name comes from oil rigs that are located in ocean and the ones that are drilling oil. And as I have said, the remaining tasks like generating the block, networking, peer-to-peer exchange, and everything else, all of these tasks are handled by the actual computer, which is running here. GPUs only handle the generation of hash values. The next step in the development of mining process was FPGA, which stands for Field Programmable Gate Arrays. And this field programmable gate arrays can perform operations according to a certain algorithm. So you see, it's not a computer anymore. They have IO bus, input-output bus, and there is a computer which runs the software for the Bitcoin node. But again, the mining process is handed over to this arrays, to this gate arrays. And interesting thing is that FPGAs don't even have the source code. They don't even really know what are they doing. So they just have the hardware, the circuitry to do certain computations, and they receive the necessary information through the input-output bus from the actual computer. They do the work and they are programmed, since they are programmable gate arrays. They are programmed to do this operation. So it even looks a bit similar to these microcontrollers like Raspberry Pi or Arduino. So example of, imagine you had an Arduino board and you program this Arduino board to do some computations. You connect it to your computer and you do the mining and get the nonce, the resulting nonce in return. And then your software constructs the block and sends it to the network. And the latest step in the mining industry is ASIC, which stands for Application-Specific Integrated Circuit. They look like that, and as you see, it's simply just circuitry. It implements the algorithm itself, the very hashing algorithm in the hardware. So all of the circuitry, all of these transistors, resistors, small capacitors, they all are arranged in such a circuit so that it doesn't even need to be programmed. It's simply it has everything it needs to implement this algorithm. It's hardware level algorithm. And when these ASICs are produced, the circuitry already implements the necessary function, which in our case is hashing the values and well, just hashing. And these miners can connect to the full nodes via internet or via some other means of connection, and they receive inputs and return mining solutions. That's everything this thing does. It gets input information, so what to hash, and it hashes, it gets what to hash and the difficulty to achieve, and it does the hashing until it matches the required difficulty threshold and returns the value to the node. It's that simple, but at the same time that complex, because it's not easy to implement all of these algorithms on the hardware, which is, I think, pretty interesting the way that it is even possible. And one also interesting piece of trivia is that actually ASIC miners are pretty good for heating, and they can be even more effective than regular heating devices, home heating devices, considering their coefficient of useful action and considering the amount of heat they produce when they work. So when just in case you don't know how to heat your house in the winter, you can of course buy a small ASIC farm, put them somewhere in your office or in your room, in your house, and have a nice Bitcoin producing heating device. So it's a win-win in a way. Also, let's talk about pools. And pools are basically not a mechanism, but a group of miners who don't have their own Bitcoin node, and they connect to a certain node which orchestrates tasks for mining among them and distributes the reward. On the other hand, when someone does solo mining, which it means that I, as the validator, I have the full node, I have the miner, and I do the mining myself. I don't connect to anyone's node. I just do this myself. But these pools, they basically gather computational power from many different miners and orchestrate so that everyone is solving this proof of work puzzles in parallel, different puzzles, different miners, and they can find the solution faster by aggregating this computational power, and then they evenly distribute the reward according to the input that each of the miners had for this pool. What is important, first of all, is that here we have the aggregation of computational power among several big pools. The biggest one is being Foundry USA, then the Ant pool, F2 pool, Binance pool, via BTC, Brains, and so on and so on. But there's also the unknown category, and these are unknown players. So they have chosen to not identify themselves. They can be either individual miners, just so this can cover some number of individual miners who do not identify themselves, or this may include some pools which are not identifying themselves. But there's nothing inherently wrong with that, because if they are still doing the adequate job, they are not obliged to identify themselves. And interestingly, the number of these unknown players is bigger than even some small pools. Now, a little bit of statistics. Electricity consumption per day of the whole Bitcoin network is around roughly 328 gigawatts. And this is a huge number. It may sound really, really big, but it's twice less than services like YouTube, for example, consume also daily. So actually, Bitcoin is consuming twice as less than YouTube's services and the whole YouTube infrastructure. But of course, it can be compared to the power consumption of a small country, probably not the country like Ukraine, but country like Georgia, pretty likely. The amount of rewards per day is roughly 21 million, and of course it's this number will fluctuate a lot because the price of Bitcoin also fluctuates a lot. The percentage of fees from the reward is 3%, and what it means is that 97% of the total block reward comes from issuance, from the block reward issuance, from the issuance of coins for mining the block. And the remaining 3% is gathered from the fees that are included into this block. And eventually Bitcoin will reach a state when this value will be 100%. So there will be no issuance and all of the rewards from the block will be 100%. Cost of one transaction for maintainers is roughly $70. And let's explain what it means, because it can be pretty confusing. This value is calculated as the total costs estimated based on the total computational power in the network in United States dollars. This includes the hardware, the electricity, plus the maintenance costs of full node. Then this total number is divided by the number of transactions in the previous months. So we gather these estimates for the months, get the full sum of the United States dollars and divide by the number of transactions. And by doing that, we roughly get cost of one transaction for how much does it cost for the maintainer, for the validators in the network. On the other hand, average fee for the client is roughly $1.25 as of 16th of February, which is today. And the blockchain size is 451 gigabytes, and this includes the complete size of the blockchain, only Bitcoin blocks. So not only Bitcoin blocks, not other things. And as this lecture is approaching its end, let's debunk some myths. Let's bust some myths. The first that we have here is if you use more miners, you can mine all Bitcoins much earlier. This is completely not true, because if you have been following these and previous lectures closely, difficulty is adaptable. So if you get your hands on an enormous amount of computing power and start abusing this computing power, the difficulty will adapt appropriately. So you cannot just mine out all bitcoins and like generate transactions every second to mine all of these bitcoins. No, the difficulty algorithm, the difficulty mechanism is configured to aim at one block roughly in 10 minutes. And that's why the difficulty will grow if you try to pour more computing power into the system. Myth number 2 is mining will stop after 2140. And this is the year when bitcoins will stop its issuance, again roughly. It's not true, because the process will remain. The mining process is the process of finding the solution to this computational task in order to add the block. So the only thing that will change is that there will be no block issuance rewards. Next, mining difficulty will only increase, and again, it is not true. The difficulty fluctuates based on what is the computational power. So, for example, some people are entering the mining business. Some people are leaving the mining business because it becomes too expensive. For example, in their country to mine bitcoins, the electricity costs are just too high to maintain the node, so they shut their node down, they don't mine, and that's why the computational power decreases and the difficulty will adapt the same. So at one point, if a significant number of validators quit and stop mining blocks, then the difficulty will decrease significantly to support this level of one block roughly every 10 minutes. The cost of Bitcoin depends on the cost of mining. In fact, the opposite is true, because the more Bitcoin costs, the more people are attracted to do the mining. And if the price of Bitcoin falls, it means that less people will want to do that, because it will be cheaper to get Bitcoin on the exchange than to mine it yourself. And again, the cost of Bitcoin as the asset is determined simply by supply and demand. So it's that simple. And the more Bitcoin costs, actually, the more people want to mine. And the last is block creation always takes 10 minutes, which is, as you may guess, not true, because it is the value at which the protocol aims, but it doesn't mean that it's always 10 minutes, because the process is random. The process of mining is random. You may it just may happen so that you will find that you will mine the block not in 10 minutes, like in 1 second. So you will have 2 blocks coming in a row with a difference of 1 second, and for everyone else it will be okay, because you are doing your job, and it's just that you have been lucky, and 2 blocks were created almost instantly, but still they go one after each other, and they follow all of the rules of the protocol and so on. But since the process is random, it's just so happened that the block creation time for you as the validator doing mining, it was less at this very given moment of time. And this is it. I know today was a rather intense topic and rather intense lecture in terms of information, but I hope you were able to take it all in and to, generate some questions from that. So if you do have some questions, let's do that while we still have some little time.
Yes, time for question. Thank you, Alex. We're waiting for your question.
I believe everyone is still processing, everyone is doing proof of work in their heads, so maybe questions will come later in Google Classroom, for example, but of course that's why we are doing everything of that, so you can reach out to us even if you don't have questions in the moment.
Okay, our student maybe mining questions now.
Yeah.
Okay, few minutes. We're waiting. So I will add all materials to the classroom and see you soon at the next week.
Thanks. Yep, thank you everyone and have a nice evening. Bye-bye. See you soon.
Bye-bye.
Bye.
Bye.